In this video, we introduce collisions between different masses. Let's begin with elastic collisions. In order to ease the mathematical assignment, let's solve the problem in a reference frame where the velocity of one of the bodies is null. To find relative velocities, that is, velocities in the moving reference frame, subtract to the velocities, in the absolute frame, the velocity of the moving frame. After solving the problem in the frame moving with body B, we rewrite velocities to keep with our frame. So, from now on, velocities are relative to a frame moving with velocity VB. As relative initial velocity of body B is null, we can greatly simplify both equations. Note that the final relative velocity of body B is not null, since its velocity change after collision while the velocity of the moving reference frame does not change. Divide second equation by 0.5 and both equations by ma. Square the first equation. Equate the second members of the equations. Cancel v relative of final squared on both members. Divide equation by mb over ma and by v relative of b final. Solve the equation for the conservation of momentum. Remember, we wrote it for the reference frame where v relative of b equals 0. We have, now, a system of equations which allow us to find the final relative velocities of bodies A and B as function of the relative initial velocity of body A. Rewrite the equations for the best canonical form of the system of equations. Solve the system of equations. You can use the known algorithm. Remember, we are dealing with relative velocities. Substitute the relative velocities by its meaning. Simplify and you are done. Our equation works for different masses and it works, also, when the masses are equal, the situation we dealt in the previous video. So, we say it's a more general solution. If the two masses are equal, the two bodies exchange their velocities during collision, as you already know. The mass of body A is much smaller than the mass of body B. We have the situation of collision of body A with Earth as body B. If we consider VB equals 0, then the final velocity of body A is symmetrical to its initial velocity. That is what we found when we studied rebound. Subtract the final velocities, VB final minus VA final. This is the separation velocity. The approaching velocity equals the separation velocity, in perfectly elastic collisions. Even when the masses of the two bodies are not equal. Observe several examples of perfectly elastic collisions between different masses. See how the separation velocity, v, b final minus v, a final, always matches the approaching velocity, v, a, minus, v, b. During inelastic collisions, the equation for conservation of the kinetic energy is of no use. In studying inelastic collisions, we use the equation that relates the approaching and separation velocities, through the coefficient of restitution. Note that this easy equation also works on perfect elastic collisions. Enough, to assign the value, 1, to the coefficient of restitution. In real life, the coefficient of restitution is lower than 1. Then, the separation velocity is lower than the approaching velocity. Observe, through simulations, several collisions where the coefficient of restitution is lower than 1, so the separation velocity will be much lower than the approaching velocity. Solve the easy system of equations in order to find the final velocity of body A and the final velocity of body B. Rearrange equations. Solve the easy system of equations in order to find the final velocity of body A and the final velocity of body B. Note that, if E equals 1, we have the equations we deduced before, the hard way, using the equation for conservation of the kinetic energy, which have lots of squares in it.
The position of the center of mass of two particle bodies, as A and B, is given by the known formula. The center of mass is closer to the body with larger mass. Velocity is the derivative of position. After derivation we have the velocity of the center of mass of the system. The velocity of the center of mass does not change with the collision. A consequence of the conservation of the total momentum of the system of the two bodies that collide.
See you in the next video.